When heavy machinery hits a massive pothole, or a building is subjected to intense vibration, mechanical shock absorbers try to absorb that kinetic energy, but there is a physical limit to how fast they can react. To alter how stiff or soft that damping effect is in real time, conventional systems rely on hydraulic valves. Because valves are physical objects, they have mass, they experience friction. They have to physically slide or rotate into place to restrict the flow of fluid. That inertia builds a time delay directly into the hardware. During millisecond-level events, like an earthquake's first strike or a tire hitting highway debris, a solid physical piece of metal simply cannot open or close quickly enough to react to the impact. But what if you could bypass the valve entirely? What if instead of pushing fluid through a mechanical bottleneck, you could send an electrical signal to the liquid itself, commanding it to become thicker? Achieving a truly instant mechanical response requires stripping away those moving parts. Engineers have to abandon traditional hydraulics in favor of smart materials, electrorheological and magnetorheological fluids. Inside these smart fluids, millions of microscopic particles, like polarizable silica or ferromagnetic carbonyl iron, float in an inert carrier oil. In their resting state, they drift completely unattached. With no structural bonds holding the particles together, the mixture flows easily, behaving exactly like regular oil. Switch on an external electric or magnetic field across that fluid, and the physics shift immediately. The field induces a dipole in every single particle. One side becomes positively charged or magnetically north, while the opposite side becomes negative or south. Operating exactly like tiny bar magnets, oppositely charged poles attract each other. The particles snap together tip to tail, forming rigid chains aligned with the invisible field. In milliseconds, these chains pack tightly, building solid columns bridging the entire gap from top to bottom. Commanding the particles to build their own internal scaffolding, engineers freeze the fluid in place, locking the machinery without ever moving a mechanical valve. Once built, these columns act as structural pillars, blocking the path. To move and slide fluid layers, the machinery must forcefully snap those microscopic chains. This chart shows the mathematical rule behind that resistance, known as the Bingham plastic model. Unlike regular liquids that flow when any pressure is applied, a Bingham plastic requires a specific minimum force to start moving, which is why the line begins high up on the y-axis rather than at zero. That elevated starting point is the yield stress. It represents the exact mechanical force required to shatter the columns and force the material to flow. The strength of those columns is determined by a strict physics equation. The interparticle attraction grows with the square of the applied field. Double the field strength, and the fluid becomes 4 times as hard to break. Because of this predictable relationship, physical stiffness is continuously tuned. An engineer twists a dial, increasing electrical current, and the hardware instantly fights back harder. While both fluid types use the same tip-to-tail mechanism, they rely on different triggers. Electrorheological, or ER fluids, use high-voltage electric fields, while magnetorheological, MR fluids, use magnetic fields. This comparative bar chart shows their actual stopping power. The ER fluids generate a maximum yield stress of around 5 kilopascals, while the MR fluids push all the way up to 100 kilopascals. That massive 20-fold increase in sheer physical strength makes magnetic fluids the standard choice for holding back the forces of heavy machinery and structural engineering. Inside a commercial MR damper, an electromagnetic coil is built right into the piston head itself. As the piston travels through the fluid-filled cylinder, the coil adjusts its magnetic field continuously, thickening or thinning the oil as it passes through the channels. By adapting the fluid's yield stress 50 to 100 times per second, this internal piston design allows a suspension bridge to absorb an earthquake or a heavy truck to negotiate off-road terrain, instantly adapting to unpredictable kinetic forces. The exact same materials are used for extreme precision. By mixing abrasives into MR fluid, manufacturers use magnetic fields to shape the stiffness of the liquid, creating a custom polishing tool that conforms exactly to nanometer-scale optical lenses. In consumer technology, smart fluids generate programmable resistance for haptic feedback joysticks, and they allow prosthetic knee joints to adapt their physical stiffness seamlessly to match the wearer's walking speed. Across all these systems, designers are eliminating the complicated networks of gears, valves, and physical linkages that eventually wear out. The real achievement of smart fluids is the ability to command thousands of pounds of macro-scale mechanical force by manipulating microscopic physics at the speed of electromagnetism.